You can start when I finish my pizza.
Yeah. Well, wait 1 minute.
Can you, I know you're gonna crop the videos. Can you keep me eating pizza in the video? Thank you.
All right, welcome everyone to our final C prime talk of the semester. Can you switch to the next slide or the previous? I forget which one. So my name is Tyler. If you don't know me, I'm a graduate student. This is Jorge. He is also a graduate student. And this is CU Prime. CU Prime is a student group which is dedicated to increasing inclusivity and diversity here in the CU Physics Department and beyond to other anyone really. And so we do a bunch of different things. We have a mentorship program. We have a class that gets offered each fall semester, and we also have a talk series. And so this is the final installment of this talk series with free pizza, where we hear about research that goes on within this department. And it is my pleasure to welcome Jorge, and I will let you introduce yourself throughout the course of the talk. If you guys have questions at any point throughout the talk, feel free to interrupt, and we'll also have times of discussion throughout. With that, I will let you take it away.
Thank you very much. I'd like to thank Tyler for introducing me so excellently. But I can do one better. My name is Jorge Ramirez Ortiz, and I'm a graduate student. I'm a second-year graduate student, which means that I started working here at the University of CU Boulder at 2021. The name of my talk is Shy and Sensitive Qubits, approaching them with superconducting microwave resonators. So I purposefully put qubits in the title because everyone loves qubits. And so hopefully I'll be able to explain to you what a qubit is and what I mean by superconducting microwave resonators. And as much as I love buzzwords, these really are all the 3 buzzwords that describe my work. I work with superconductors, I work in the microwave frequency regime, and I work with resonators. If you don't know what those terms mean, well, I have some news for you. We're going to go through them today. So a brief introduction to myself. I'm a second-year graduate student, and I put second year in quotation marks because of a reason I'll explain in a little bit. I am Latino identifying, and my pronouns are he, him. My family illegally immigrated from Honduras, which is a country in Central America, when I was 1 year old. And because of that, I was the DACA beneficiary until I received my US residency in 2018. I went to the University of Maryland, College Park for physics from 2017 to 2021. And that was by complete accident because I grew up in Maryland and I decided I want to do physics randomly. And then it turns out that University of Maryland is actually like huge for physics, on the East Coast at least. So a quick timeline of my undergraduate career. In 2017, when I was a high school senior, by complete chance, it was like a friend of a band teachers of a friend, graduate student, my coworker. I managed to connect with one of the professors at the University of Maryland, and he gave me a project where I measured pedestrian bridge oscillations using a Raspberry Pi. And he kept using really complicated words like Fourier transform and oscillations and mechanical vibrations that I really didn't understand as a high schooler. But I got to play with electronics, which I love. I got to code a lot, which I think is awesome. I got to do a lot of circuit wiring, and I got to attach really suspicious looking things to bridges, which was a fun time as a rebellious high school teenager. In 2018, so that was my high school senior year, and when I started college, the summer after my freshman year was 2018. And I got a internship with a group that works for LHC, which is the Large Hadron Collider in Switzerland. And the University of Maryland has a group dedicated to that, at the time was dedicated to upgrading the LHC-B experiment. And so what I did was absolutely nothing to do with particle physics. I got really, really expensive circuit boards, and I used really, really expensive oscilloscopes that made me sweat every time I used them because they were so sensitive. And I did a lot of testing and Q&A, and then I also coded a little bit of Raspberry Pi monitoring software as well for the testing they were doing. And so I wrote 2018 and 2019 because I started with them in the summer and they paid me, and then they realized that I was valuable enough that I didn't deserve pay. And then I worked with them throughout my sophomore year. Then with all the research experience I had, my resume was looking pretty sweet. I managed to land an internship for the summer of my sophomore year at Caltech LIGO. That was a complete surprise to me. I don't know how that happened, but it was a great experience. I visited Pasadena, California, and they flew us out to Livingston, Louisiana. I stepped off the plane in Louisiana and decided that was my first and only time I was going to be in Louisiana because it was disgustingly humid. Unfortunately, the group I was assigned to is really toxic. The professor that was in charge of getting all these REU students played favorites and stuff like that. So definitely was the start of my imposter syndrome that still persists to this day. You'll notice from the self-deprecative humor that seems to plague my existence. And I really like this chip right here because it explains how a gravitational wave is detected. And it uses the exact same kind of physics that happens in my line of work, except they're working in an optical regime. So they're using EM waves that are in the terahertz frequency. So each of the particles of the photons in the light oscillates at like 10 to the 12 hertz or 10 to the 12 times per second. And my work is microwave regime. So instead of 10 to the 12, it's 10 to the 9. And it turns out that exponential factor, or the number in the exponent, matters a lot for the kind of physics you can do. So after that, I came back from Pasadena, and then I was ready to really go and try hard to find a research group for the summer of my junior year and senior year that really applied to the work that I wanted to do. But junior year summer, I took a break and I just worked at my lab. And then so senior year summer was going to be it. Turns out the world got infected with a plague. So I somehow, after having a couple REU offers, they all got canceled, which was really suckish. But it turned out to be fine because my mentor connected me with someone in Georgia who was at the Georgia Tech, and they were working in chaos theory, which I would love to give a talk about, but I was only given 45 minutes. So they worked in chaos theory, but specifically they worked in cardiology. And it turns out that the way your heart works has a lot to do with chaos theory. And so I was tasked with doing numerical analysis of differential equations, which is really fancy talk for I went into the computer, coded a bunch of arrays and had them do really fun things. And then I got an electrocardiogram out of it. And then in this plot, you can see, so I made a one-dimensional tissue of heart cells, and each heart cell has a different property that allows it to contract or expand at a specific rate and hold itself for a specific time. And this is what causes your heart. Because I mean, if you think about it, they're all spatially separated, right? Your heart is not a point-like object unless you're a physicist, but these guys are also biologists. So the heart is a tissue and you need all the cells to contract in a specific order, and that causes the pumping. So it's really complicated. And this is something that really gave me an existential crisis. But the model that they used was this many differential equations with this many parameters and this many different types of cells. So I had a fun summer trying to put all these numbers into these. And then also it was in JavaScript. Yeah, the reason they told me it was in JavaScript was because they wanted to use OpenGL, which is a way that web browsers can use the graphics card. And so like they sold it to all the grant funding agencies by like, oh, you can do heart model simulations on any different type of device as long as it has a graphics card, which was fine, but it was awful. So moved on from that. I really liked this plot, which showed the original thesis that I modeled my differential equations after, but only in one dimension. These are two-dimensional versions of that, and you can see the chaos theory in that a small deviation from the original initial condition. So these are coherent, which means that, I guess in a simple way, they make sense according to the model that you have, but these start to mess up as soon as you have some kind of stray electric signal or something in the heart. So this means that you're having a cardiac arrest and you need to hope that someone has a defibrillator nearby. These mean that you are, in fact, having a beating heart. So that was my undergraduate experience. Now, graduate school, I applied to only 6 graduate schools because I was burned out from the pandemic and I was overconfident and I was broke. I had an interview with MIT, but I got distracted and talked about diversity, equity, and inclusion too much because they kept asking me questions about it. And so by the time the interview ended, we hadn't talked about any physics, so I didn't get the position. Fine, because MIT sucks. I had an offer, well, I didn't have an offer from UMD and CU, but for CU, I was on the wait list. For UMD, I had access to the logs because they had an oversight. So I saw that they had me on a wait list, but they didn't have money for me. In that situation, you have to find a professor who will fund you. I had someone at UMD who was willing to fund me, and coincidentally, they also worked in superconducting qubits. But I hated College Park. I was sick of the city that University of Maryland's in. It's a crap show. Even if my family's there, I needed to go. So last minute CU accepted me, so that's where I am today. The first year, right before I came to Colorado, I had a really bad case of the shingles, and it was on the top right of my head, which is a really sensitive area because your brain and your eyes there. And so the doctor that saw me told me I had an allergic reaction, and I went home and it got worse. And so now I have permanent nerve damage. So I wanted to bring this up because this is the reason why I consider myself a quotation mark second year graduate student. Because my first year was terrible. I failed both my classes because I couldn't make it to my finals. The spring semester of my first year, I took a lab from an engineering course that I really should not have taken. It was not easy. And so I started really strong undergrad, and then I tripped and fell, broke my face. But now we're back. We're doing good now. So life goes on. I survived 14 hours driving here somehow, and I see a neurologist regularly. So things are going great. So the end of my first year in August, so my first summer as a graduate student, I was desperately looking for labs because you're given a timer to find a lab and it's really stressful. So I had maybe 15 calls for applications show up in my email, and I cold email maybe another 10 labs. So I had about 7 interviews. I spent my fall semester of my first year on rotation with a professor, and that didn't work out because I didn't really like the research. And I finally landed a position at NIST with the Superconducting Electronics group under Peter Hopkins, who's my PI, and Sam Benz, who's like the division chief. So I have a lot of bosses. I guess that's how it works in the government. I had a really good first impression of them, and they seem really down to earth. So that's why I decided to join their lab versus anything else. Okay, now it's time for some physics. Now we're over with the introduction. You guys know me as well as I know myself. So first, qubits, all right? Qubits are cool. Everyone loves qubits. Everyone wants to learn about qubits. If you don't want to learn about qubits, what are you doing with your life? Qubits. But first, you have to start with bits. Okay. Why is it the way that it is? Right. It's a Q stands for quantum, and bit stands for bits. Okay. So a classical bit, we can imagine it as some sort of system where you have a 0 and you have a 1. Okay. Now that is incredibly vague, and for a good reason it's that way. I even went and drew these like weird looking brackets around them. And I did that in a suggested way because it's going to relate to quantum bits. But first, classical bits. Imagine a computer. Computers have electronics and they work with electric signals, but they need a way to separate true or false. Or say you have a memory. Did something happen or did something not happen? A physical example would be a capacitor, right? If we have a capacitor, if it has no charge, we can label that as 0, so lack of charge. And if it does have a charge, we name it a 1. So that's a 1. And that's why you see computers like that funny looking 0s and 1s falling from the sky. That's the idea of a bit. 0 or 1, on or off, so on. A quantum bit is the same thing, except it's no longer just a one-dimensional on or off. It can form any 3-dimensional composition of 0 and 1. And that sounds really strange because it is. And really the way that it works is that we have this equator, and we can label that as complex superpositions of 0 and 1. Now I'm starting to throw out the buzzwords, so I'll try and break it down a bit. So imagine if you have 0, and then you have 1 as your y-axis, as your z-axis. You can think of the x and y axis as like, imagine if I put an imaginary number on one of these and then added them together. So 0 plus I1, or I0 minus 1, or something like that. We keep track of the complex number as, we call that a phase. And it's starting to get a little jargony. So let's go back down to basics. So some examples of classical bits working with classical systems. I talked about capacitors. One thing is interesting is CDs. They have magnets on them. And whether the north pole of the magnet is upwards or downwards, that's the 1 or 0 for that system, which is really cool. Some examples of qubits include atoms with electron orbitals. So we can say, is the electron in this orbital or this orbital? And whether the location of the electron is 0 or 1, or some complex superposition of that. Remember, complex superposition just means that one of the 0s or 1s has an I in front of it, or some, number of magnitude of I. I work with Josephson junctions, which are superconductors with not a superconductor in the middle. So whatever that means, that's what I work with. And then there's also photonic qubits, which use photons, and whether they arrive early or late as their 0s and 1s. So the title of my talk was Superconducting Qubits Shine Sensitive. Well, why are they shine sensitive? Well, shy, I interpreted that to mean hard to communicate with. And sensitive, I interpreted that to mean easy to be disrupted by their environment. So shy qubits are shy. What I mean by that is that they'll only respond to coherently to specific frequencies. And the word coherently is really important. Coherently, again, that just means something that makes sense. So I don't get a bunch of jumbled nonsense back when I talk to my qubit. My qubit is designed to only work with the specific frequency of the signal that I send it. Okay. Sensitive. So sensitive means easy to be disrupted by the environment. And sensitive is like 90% of quantum mechanics. Like, how does my system respond to specific situations and scenarios? And what happens if I have this potential versus this potential? What happens if I want to do time evolution of this thing? How does that affected by its environment? And a consequence of that being sensitive is that it's only resonant to specific frequencies. So both of these characteristics imply the hardest thing about quantum experiments. And I wrote something in red here, but the lighting makes it awful. So maybe only the people on Zoom can see it. It says, how do you communicate with your qubit without introducing noise from the environment, right? So I want to communicate with my qubit, even though it has only specific frequencies, but how do I do that without introducing noise from the environment? So for the first discussion, talk with your neighbor for a few minutes. What would make a qubit shy, so it's hard to communicate with, and what could make it sensitive? Go ahead. Okay, so let's bring it back in. So, I heard some good discussion. The idea that I thought, and these are not obviously the only things, but things that make your qubit hard to communicate with means I thought about noise from the environment. So say someone's phone is ringing in the middle of your experiment. That'll introduce electromagnetic waves that might interact with your qubit. Noise from measurement devices is a really big one that you don't think about as an undergrad because it's been solved for you. But when you're starting to design your own experiments, you need to figure out like, okay, well, my oscilloscope, and this is a problem that I had, my oscilloscope likes to scan from 4 to 8 gigahertz. And at 7.1, it has a huge noise limit or a huge noise signal. Like, why is that? You know? So that's something that has to happen. You have to think about. And if anyone said this, I'll be really, really impressed. But noise from intrinsic quantum uncertainties is a big one. If you have quantum systems and they're quantized, meaning you can only, count individual pieces, individual particles, because you can't exactly know where your position is if you have a really good grasp on your momentum, or you can't know your momentum if you have a really good grasp on your position, that can cause situations in which you can't measure beyond what we call this quantum resolution limit. So yeah, I wrote bonus points because that's not something you really talk about in quantum unless, it's the end of the semester and you've already checked out and they mentioned this in your class. Okay, sensitive. So what would make them sensitive? Thermal noise from wires is a really big one for superconducting qubits because we try and cool our qubits down to the millikelvin level. So I'm just going to make numbers up. I'm pretty sure the temperature of vacuum is like 4 Kelvin. And you're making a face. Is it not 4 Kelvin?
What vacuum?
Sorry, of space. Space, yes. I said vacuum thinking space. This temperature of space is about 4 Kelvin. Our dilution fridge can go down to about 4 millikelvin. So that's like 10 times, 40 times. I can't do that in front of people. So thermal noise from wires is really big because room temperature is 300 Kelvin. So imagine all these atoms wiggling about at 300 Kelvin, whatever units to temperature they're wiggling about. But like as we get down to the 4 millikelvin level, the atoms have stopped moving. Physics has effectively paused. If you send an electrical signal down from the top of the fridge at 300 Kelvin down to your qubit and it's hot, you want to filter out all that noise that's coming from the atoms wiggling. Vacuum fluctuations are really interesting. They're not particularly applicable in my case, but in some situations, the vacuum, if you've watched any like Stephen Hawking talk where he talks about virtual photons, that's illegal outside of this room. Don't talk about virtual photons. People get upset when you mention them. The virtual photons are running in and out of existence everywhere, and that can interfere with certain experiments. And another thing is how well do you know your parameters? And these two topics are kind of intertwined, I'm sure you could tell. But how well do you know your parameters is kind of related to your measurement device noise. Like, am I certain that my signal is exactly 5 gigahertz? Am I certain that my qubit was manufactured to be resonant at 5 gigahertz? Who knows? All right, so this is a commonly stated joke in graduate school. Everything in physics is either a two-level system or a harmonic oscillator. And if you don't know what that means, that's totally fine. That means you've been spared from this horrifying truth of the universe. The good thing is that as a physicist, when you go into graduate school, you pick research, you only have to be an expert in one of them. Unfortunately, superconducting qubits are both two-level systems and harmonic oscillators. So, hooray, I have twice as much physics to study as everyone else. At least that's what it feels like sometimes. So we'll review really quickly harmonic oscillators. So a classical harmonic oscillator, I've Googled the harmonic oscillator and pasted it on the slideshow. This is a potential energy graph of a harmonic oscillator with a spring as like an example of a harmonic oscillator. It's not the only harmonic oscillator, but here we are. So the vertical axis tells you how much energy you have if your system's at that point. So if I'm at point number 5, I'm very much extended. I have a lot of energy. And you could do some kind of gravity analogy and say, if I put a ball here, it's going to want to drop all the way down. That's how much energy it has. So that's a classical harmonic oscillator. Quantum harmonic oscillators are a lot more fun, as you can tell by a diagram. If you have no idea what's going on, that's totally fine. I didn't until a couple months ago. But the idea is that you suddenly have, instead of a ball rolling down a hill, you have a particle stuck in a harmonic oscillator potential. But the particle can only take wave positions. So this wave, depending on what level you're at, you have level 0, which is the lowest energy, the lowest part of the well. We have level 1, which is the second highest, right? It's level 1, second highest, whatever. Third, fourth, fifth. And then this comes out from Schrödinger's equation, which I'm starting to get off the rails here. So this is the quantum harmonic oscillator. All you really need to remember from this is that we have the same exact potential energy as the classical and as the quantum. We have an 1 over or x squared over 2 potential, but suddenly we have the fact that we're quantized. So we have level 0, level 1, level 2, level 3, instead of being able to take any in between. Okay, so now I've taken the quantum harmonic oscillator and a superconducting qubit side by side. And this graph is really, really busy, and I promise it's the most complicated of talk. But the quantum harmonic oscillator here, you have level 0, level 1, level 2. As I showed you before in the previous, okay, it's not having a good time. Okay, so I showed you before level 0, level 1, level 2. And now I'm showing you the same exact diagram, but you are having a great time. You're now spaced, you're the same thing, but you're spaced by h bar omega. And h bar omega is the unit is energy. So just think of it as 1 energy, 2 energy, 3 energy. So when I mentioned earlier that superconducting qubits are sensitive, we want to be able to specifically have just the bottom and the one above it. So that's what a two-level system is. We want to isolate our experiment to just the first level and the second level. Now, you can't do that with a regular quantum harmonic oscillator because they're all equally spaced. You don't know if you're at 0 or 1 or 2 because they're all the same energy. So when I throw a 1 unit of energy, h bar omega, at my system, it'll jump between, I don't know which ones it could jump between because they're all equally spaced. But for the superconducting qubit, suddenly by introducing some fun superconducting physics, I can change the distance between the energy levels. And I'll have 1 unit of energy here between 0 and 1, and then a different energy unit between 1 and 2, and so on. So you'll see that the x squared potential overlaid the transmon or the superconducting potential. So that's why superconducting qubits are really helpful, because instead of having a quantum system with equally spaced distances between energy levels, we now have differently spaced energy levels between them. So wait, I mentioned microwave resonators. When do those come into play? Well, we want to isolate our quantum system, but we still want to communicate with it. You might think of isolation as like the perfect scenario in which, okay, I have no noise, I have no anything, my quantum system is my quantum system. But if it's perfectly isolated, you also are part of the environment, you can't communicate with it. And, sometimes the environment does really cool things. So microwave resonators allow us to control exactly how our quantum system communicates with the environment. It's kind of like throwing our qubit into the closet and only allowing like a mailbox, and we send information in and it sends information back out. So here is a picture of a superconducting qubit, specifically the transmon. Let me be more specific. This is a picture of a chip with a superconducting qubit on it. This right here is our qubit. It's a transmon. So all you need to think about is that potential well that I showed earlier. This resonator right here is this long squiggly little thing, and it connects from our input and our output. So we send a signal in through the top, it goes through the little wiggly thing, and then talks to our qubits. And then the qubit, we measure the reflection, and it comes back out and into our output. So that's exactly how our measurement setup works at my research group. So what I'm going to talk about is the resonator now. This is the most important part of our system, minus the qubit, I guess. The resonator is like, if you imagine a chip, it's a little cutout in the chip that looks like this. And we call it a coplanar waveguide because it's coplanar, meaning it's flat. It's not got any dimension to it besides flat. And also, it's a waveguide, meaning all our electrical signals, which are just electromagnetic waves, they're guided along this like track. And it's considered a transmission line because there's two of them side by side. If you have ever heard of transmission lines in your waves class, I ignored all of that and I regretted it. So I was like, who needs transmission lines? I'm not an electrical engineer, but anyway. So our qubit is sensitive because our resonator is not perfect, right? We have to place the resonator onto a chip, and the chip has a substrate underneath of it. And so this substrate, we have electromagnetic waves traveling through our waveguide. They interact with all the atoms inside the substrate. And so because there's an electromagnetic field, our atoms want to align themselves. This is physics 2, right? And so the fact that we're going from this system, this state to this state means we lose energy. Any energy loss that you have in your system is a source of information loss. So yeah, it's a parasitic leakage of energy. So we're losing information, and that's why our qubit's so sensitive. That's a reason, that's a source of where our sensitive qubit could get messed up by. I drew a picture, I keep saying that. I'm taking credit for these things. I copy pasted a picture of electromagnetic wave to remind you that electromagnetic waves are both waves, and you can imagine them as a wave with E and B field, or you can imagine them as a charge just moving. And the movement of these electric charges causes a wave to propagate. And so that's relevant because in our system, we have some atoms, right? And there's electrons between the atoms. Well, our electric signal traveling down our wires and down our system, all the movement of that stuff causes the electromagnetic waves to bounce around. And that could be another source of sensitivity for our qubits. Right, so microwave resonators again. What would happen if I placed a bit of light between two infinitely reflective mirrors, between two mirrors with a finite reflectivity? And to define a reflectivity, every time the light bounces between the mirrors, if it's 100% reflective, none of the light is lost. And if it's finite reflective, then you lose some of the photon. And then how might that be useful? All right, so go ahead and take a minute to discuss that. All right, let's bring it in. So before I start talking about the answer to this question, remember that light is just electromagnetic waves, right? And electromagnetic waves have frequency and wavelength, which are inversely related. So for very low values of frequency, we call those radio waves. Low frequency means they oscillate very slowly, but the speed of light is constant. So when it travels really slowly, it has a really long wavelength, right? So the distance between the peaks is really long. And the opposite happens when you have really high frequency light. Really high frequency light goes like really fast, like this. But because it's going really fast, the distance between the peaks is really short. And so when you have radio frequency, like electrical engineers, you can take a lot of approximations by saying, okay, my frequency is really low. I'll just ignore this extra term. Same thing with really high frequencies. Really high frequencies, you're like, okay, my frequency is really high, my wavelength is basically nothing, so I'm just going to ignore these terms. When you're in the microwave regime, this is visible light. Microwave regime is right here. you can do neither of those. Things get more complicated. So you can't just Taylor expand everything and get rid. Well, you still Taylor expand everything, but you can't just get rid of things. Okay, so back to the question. This is something I drew. I'm very happy about it. I drew this set of mirrors, okay, and in these mirrors, I put a piece some light, and I haven't told you which way the light's going, so let's assume it's going both directions. Now let's call our reflectivity of our mirrors Ri and Re, and I think I chose this as a sophomore because Ri is incident and Re is end. So, and I'm sure that some of you have imagined what it would be like to be stuck between two mirrors, right? This is a realistic picture where you have finite reflectivity. So you see the image gets darker and darker as you go further into the mirror dimension. Okay, so that's an example of finite reflectivity. So now I've drawn a little bit more complicated. We label our electric fields because of E and M. Pick E because we like E better. You have incident electric fields and reflected electric fields. You have the ones in the middle, and you have the transmitted ones. This is the work that I did at LIGO, and it's relevant here because this is a resonator. We call it a resonator because the electric fields are resonating between the mirrors. And if you meet a condition with the wavelength and frequency, then they get stuck inside and they resonate forever, or as long as your reflectivity lets it. This is a plot from my sophomore year internship. This is showing you, well, what if my reflectivity was 0.8? This is how your transmitted light would react to that resonator as a function of how far apart the mirrors are spaced. So you'll see for 0.8 reflectivity, we have really fat, like leaky resonators where a lot of the light that's not exactly on resonance can still get inside. And a lot of the light that is on resonance still gets stuck inside, but you have a lot of extra light. And then if I increase my reflectivity to 0.95, well, these Lorentzians, as we call them, these Lorentzians get really skinny and no more of the non-resonant light can leak in. We're very, very, very sensitive to the frequency of our light. And why is that? I really like this picture that my graduate student, when I was an undergrad at that place, I had a graduate student assigned to me because the professor didn't want to deal with me. So the graduate student showed me this diagram that he made where you have this specific frequency of light. Its amplitude's really small, but it gets really, really amplified inside this resonator. And that's because you can fit exactly an integer number of wavelengths between the mirrors. So that's the condition. This could be made of lots of different frequencies superimposed on top of each other, but only the resonant frequency can be inside. And that's what is defined as a resonator. So again, this GIF, yeah, sorry.
What was the F?
Oh, of course. The F, this fancy F stands for finesse, and it's a parameter that describes how good your cavity is. So if you have a resonator, cavity is a interchangeable term. If you have a really good cavity with really good reflectivity, you have really sensitive to the frequency. And the reason we use finesse instead of reflectivity is because how sensitive your cavity is also a function of things beside your frequency. So it encompasses more parameters. So I put this GIF back again because these are the resonator number 1 at LIGO and resonator number 2. If the distance between the mirrors change, then the difference in the photodetector sees when they're put back on top of each other. So if it ever misaligns because of some gravity wave, then they'll know. That's how it works. So really, really cool GIF. So this is a microwave resonator. This is exactly the coplanar waveguide that I showed you on that chip before. And the way that it works is the exact same operation, except instead of mirrors, we have little gaps in the chip or the waveguide. These gaps act like mirrors for for electromagnetic waves, and it will trap specific frequencies depending on the gap and depending on the distance between the transmission line. And this is a circuit schematic of the transmission line. So you model a transmission line as a series of inductors and capacitors, and then the qubit that usually is in the dead center, the qubit would go here, and then you keep going forever. All right, so back to the picture. Yeah, so this readout resonator, this resonator that's so squiggly, it's squiggly because we need to fit a certain length of resonator, but we only have like a centimeter of chip. So we wrap it on itself, and that also kind of cancels out some of the parasitic effects. But yeah, same thing, resonator. And I put this here because I was going to make a point again about radio waves are in the kilometer wavelength regime, and the lasers that we use are in the hundreds of nanometer range. And that's a huge difference, but we're right in the middle where we have microwaves that are a centimeter wavelength. So if my whole chip is a centimeter long, well then my wave is going to oscillate like this, but like it's not always going to be the same phase. So it might bounce back and be a trough when it used to be a crest, and then bounce back and be a crest when it used to be a trough, and that really messes up your experiments. Okay, let's continue onwards. Oh, I'm going backwards. Fantastic. All right, so that's all the physics. Now I'm just going to talk about my lab. This is a dilution fridge. This is how we get down to 4 millikelvin. You have you have liquid helium mix that's continuously pumped throughout the fridge, and it's kind of like a refrigerator, hence it's called a fridge, where you use the same coolant over and over. If it's much better than other solutions where the coolant that you use is expended and you have to keep buying liquid nitrogen or liquid helium or whatever. This liquid helium almost never evaporates or goes away, so we can use it forever, which is really nice. But you have a really small amount of space inside. So this little metal can here is where my qubit is held. It's about this big, and we have a really small space to attach our qubits because again, the vacuum can is not very big. Here you'll see as you start from the top, you start at room temperature, and then this stage is 100 Kelvin. This stage is 10 Kelvin, and then below this is all 4 millikelvin. So it's iterative on itself in temperature. Question?
So how many does it fit in the bottom?
So inside, I actually don't think I have a picture of the inside because these pictures were from like 2 months ago. But it's like maybe the size of this thing, and you can attach something to both sides of it. So generally, we keep it to only 2 experiments or 2 chips on each side.
2 qubits.
Yeah, 2 qubits. So the chips include the qubit, the resonator, and we also don't want to cram them because they can start to mess with each other. So we restricted to 2 experiments at a time. This is my measurement setup. I'm really proud because it was already there, and I connected this wire and this wire and this wire and this wire and that wire. So I did a lot. Okay. This is my vector network analyzer, which I can send a signal to the vacuum can. I get a signal back, and then I measure the ratio. So why is that important? Well, because I want to know if I'm on frequency, if my frequency is correct. If my frequency is correct, all my signals should go into the can and stay there and be stuck inside the resonator. And then I should measure very much lower amplitude. It's not going to be 0 ever because my resonators are imperfect, but I will measure what the difference is at an amplitude. I mentioned that, or I wrote down that I have a couple things like a switch that lets me switch between experiment 1 and experiment 2. And then I also have a variable attenuator because right now I'm doing experiments to see how the qubits react to different power levels. Here are more pictures. Here are the wires I connected, and more wires, and so on and so forth. This is a schematic of our experiment. So we have an input line, and these attenuators are resistors that work on a logarithmic scale. So a 20 decibel resonator reduces my power by a factor of 10 to the 2, so 100 times. And a total, I think, of about minus 65 decibels of attenuation. Because like I said, I don't want my room temperature noise to reach my qubit. And then I have the opposite happening here where I have these really fancy amplifiers that give me about 80 decibels of amplification. So at the qubit, I should be working at the single photon level. So about minus 160 dBm. dBm are a really weird unit that no one, well, I don't understand them. Everyone else does, but it's like a decibel but fancier. Okay, this is a picture of the chip that I was working with, and it's a really terrible photo because I didn't take it. If you look really closely, I don't have a qubit on here. I have microwave resonators, and they're all like slightly different length. So squiggle, squiggle, squiggle. These parallel lines are wire bonds. We use them because our wire bonds, so we have a transmission line that's just 2 straight lines. But because we're in the microwave regime, the ground on the top is not the same as the ground on the bottom. And so we attach these wire bonds to equal the ground out throughout the circuit. And this is the box that we put the resonator chip in. This is a scan that I took my very first plot of data. I used the vector network analyzer to scan from 4 to 8 gigahertz. So I said, okay, I'm sending a 4 gigahertz signal. What is my response? All right, 4.1. What is my response? 4.2, all the way to 8. And you'll see these vertical lines are dips that show you at those specific frequencies. That's where my resonator was like, give me all that frequency. I'm going to keep it for myself. And then you see the amplitude, the magnitudes on the Y scale. My amplitude really goes down. And so these are really, really deep because they're very, very, very high coupling constant. So these are very well connected to the resonators, and these are not very well connected to the resonators. And we do that because we want to measure how good the resonators are. We want to have a picture of them at low power and high power. So that's why they're different. Question. Is that reflection or transmission? These are reflection measurements, S21. So we measure the ratio of channel 2 to channel 1, and we measure the reflection. He's trying to trick me, that's why. This is another plot that I took. I measured one chip at very low powers where we have either 1 photon here, 1/10 of a photon here, or 100th of a photon. And if that doesn't make any sense, remember that photons are also waves. So the amplitude of the wave inside the resonator is 100th the amplitude of a photon. And it's really weird. I definitely agree. And this is all the data that I took, and it shows you the reflection coefficient of the S21, and you'll see the dip right here. And the line width, which tells you like how wide is this, is 250 kilohertz. So let's do some quick math. It's 250 times 10 to the 3. My signal is 5.7 10 to the 9. So it's 10 to the 6 times 200 order of magnitude. So it's about 0.1%. So the width of this is about 0.1% of the entire frequency. So that's how sensitive our microwave resonator is. And this is like it's not necessarily a good one. It's just one that we have. Last plot that I have to show. This is data that I took and I'm going to present next week to another professor. The idea is that we have different resonators that I showed you labeled 1 through 8. And this is unfinished. That's why it's like really crappy. The idea is that at low power, at really high powers, our Q factor should be really high. So it's 1/Q. So really low means we have a really good resonator. And as it rises, we should see that it saturates. So we should see kind of like a flattening of the curve at very high powers and very low powers. And the reason starts to get into more complicated physics about all our 2-level systems being saturated at the top and all of our resonators being overpowered at the bottom. Question?
So is the Q factor, is that different from the F finesse? They're the same?
That's an interesting question. Finesse is only used when it comes to optical resonators, as far as I'm aware. But Q factor kind of tells you the same thing at a glance. But as for the actual mathematical difference, I'm not sure. I just know that both are parameters that tell you how good my resonator is. I'm sure that someone who's an expert in those will be. Question?
Yep. Oh, I was waiting for you to finish that first.
Oh, I mean that was the end of my train of thought.
Okay.
Yeah, I was starting to ramble.
What's the difference between 4 purple and 4 gray?
Okay, so starting to explain the plots instead of telling you about the curves. Each color represents a resonator. So I numbered them 0 through 9. And so the reason why they're duplicated is because I took the data multiple times. So resonator 4 purple is resonator 4 purple, and then I took the data again because my advisor was like, you didn't take enough data, we need to lower the power. And so I did another data take, and they were like, why are you taking so long? You took a month to do this. And I'm like, oh man, sorry. Yeah, so duplicate is the same resonator. The number refers to the resonator. This one's really interesting because something weird's happening to this resonator number 0. It's way above the rest. So okay, let's get away from this plot. It's terrible. Now to finish off the talk, let's talk about a day in the life of a physicist. So my ideal schedule involves waking up around 7 or 8 and getting to the office. And I want to be in the office by 8 a.m. I try and use all that time in the mornings to read for my literature review with my advisor. I read for my journal club. I read for class. I do a lot of reading. And I also have meetings during that time. It really helps me to have a fixed schedule so I know like if I'm behind or ahead. So I try to work from 9 to 11 on research and lab work only. So I know like, okay, I'm at making good pace, making slow pace. Starting at 11, that's where I want to shift gears because I've been working on the same thing for too long. I like to switch. So at 11, that's when I'm very flexible. I'll probably have my homework to do. Maybe I'll continue working on my research because I'm on a roll. That's when my meetings are, really important meetings are. And then around 1, I let myself have time to go to campus. I used to bike, I don't bike anymore. And then after class, I also have more flexible time, do homework and so on. And I really hate working on the weekends, but I force myself to work Sunday evenings. And so that helps me get back into the groove when it's time to go back to work on Monday. Oh, this is the wrong, I'm supposed to do before. A realistic day. So what I showed you was my ideal day. That's nowhere close to the reality. I'm terrible to keeping with things. I think this schedule I followed for like a week. So a real day in my life involves I have breakfast in the mornings with my fiance, or I go to the gym at 5 in the morning with this guy and this guy. In either case, I'll get to work around 8:30 or 9. I call my mom usually, or sometimes she just calls me. She always calls me. My mom calls me usually in the mornings when I'm driving to work because she's on the East Coast, 2 hours behind. I stay in the parking lot until 9:30 because I don't want to hang up on her. So I get to my office at 9:30. I check my emails, check my bank accounts, literally anything but work. It's called procrastinating. Then at 10 a.m. I'm like, oh man, it's already 10. Okay, let's do some work. So I'm really productive from 10 to 12. Like I've been talking about how lazy I am, but 10 to 12 is my best productivity time. So that's when I do almost all of my research. And then I'll eat lunch when I realize I haven't eaten since 5 a.m. or I realize I forgot to bring it. So that means I pass out around 12 either way. That's when I realize I need to put more coffee. And then with the coffee, I can maybe like 60-70% efficiency work from that time. And then I go to class. And then after class, I almost always immediately go home because I'm tired. But usually when I desperately need help on my homework, I go to the TA office and ask them for help. And so on and so forth. And then in the late evenings, I usually just play video games. Or if I have a deadline, I work on that deadline. So yeah, that's it. Thank you very much for coming to my hour talk.
Great. Yeah, so we have this QR code and a link. You can scan that if you want to provide feedback. We're always looking on ways to make these talks better. And if you're interested in helping with future CU Prime talks, there are no more, at least for this semester. So I guess that's kind of outdated. But I'd be happy to talk to you if you want to start getting involved summer or next fall as well. And we have plenty of time for questions. So yeah. I will let you lead that.
Cool. Questions.
Anybody have questions? Yeah.
Question? Yeah, totally. The fun slide that is eye-opening. So I don't know this one?
Yes. Well, in our class, we see square box with that in it.
Okay.
Where's the problem?
So that's a really good question. So you're talking about the infinite square well. Oh, sorry. Okay, repeating the question. Very good thing to do. So the question was, what is the difference between this harmonic oscillator potential with these squiggly wave functions versus the wave functions that you see at the beginning of quantum where you have an infinite square well. So instead of a parabola, you have a square well. So that's a really good question. And since you're in quantum, I can tell you a little bit more in depth. The idea is that this is our potential function, right? So when you solve Schrodinger's equation, you have T plus V, right? You have the H squared, K squared over 2M plus potential. So in the case that you have an infinite square well, it's either 0 or infinity, right? But in this case, it's either x squared over 2 or it's just x squared over 2. Sorry, I was thinking yes and no. All right, so infinite potential well, infinity or 0, here the potential is just x squared over 2. So what that causes is when you solve the Schrodinger equation, you have different boundary conditions, right? The boundary conditions before are infinity or 0. Here it's just one continuous function. So literally what the difference is, when you have an infinite square well, you can use sines and cosines. And you can just superimpose them and take whatever combination of them, whatever Fourier series you want. For the harmonic oscillator, these are Hermite polynomials. They're not sines and cosines. So Hermite polynomials are really, really weird, polynomial series, and no physicist since the 80s really wants to use them. Wants to calculate them explicitly. So you just write H. You write H0, H1, H2, H3, and so on. Does that answer your question? It was a little.
I guess my other question would be, the word like those outside of the possibility.
Yes, exactly. So the question was, is the part of the wave function outside potential classically forbidden? Yes, that is the definition. So if you have an infinity potential, no, nothing is allowed to tunnel out, not even quantum, it's infinity. You're not tunneling. For this potential, the potential is finite. So whatever is outside the potential is something that would not happen in the classical case. So this ball would not fall out of the potential. But in quantum mechanics, it would, whatever the square magnitude of this section outside, that's the probability that the particle tunnels out of the well. So I guess you could think of it maybe in like a more non-quantum case. You could think of it as like literally a well, maybe, and it's full of water, and maybe the water can leak out depending on how high it is. That would be one way to think about it. That was a terrible analogy, but there you go. Question?
Yeah, so going into quantum, how much effect does it have on research? It seems like you're dealing with some pretty small circuits, and some pretty interesting oscillating things like this.
That's a fantastic question. So the question was, speaking of quantum tunneling, how does quantum tunneling affect my research? So here's the potential for a transmon, right? Let's see. So if I have my system in the ground state 0, and I excite it to the first energy excited state 1, that means that I have a specific amount of energy h bar omega 0, 1. So when it comes to quantum tunneling, I have an answer in my head, but I don't know how to find. Maybe there's a different plot that I could look at. That's a good idea, except it's not. I don't think that would help very much. Okay, so I didn't want to talk about this. This is one of my extra slides, but it seems like you guys are very advanced, so we're going to talk about some advanced things. My qubit is a Josephson junction. Is 2 Josephson junctions of the capacitor shorted to ground. So a Josephson junction is what a superconducting. That is the most fundamental superconductor. And a Josephson junction is just a really fancy way of putting a superconductor, something that's not a superconductor, and then another superconductor sandwiched together. Okay, so the way my qubit works, we talked about some examples like trapped ions. You measure the spin up or spin down. You could talk about electron orbitals. You measure, is it an electron orbital number 1 or is it number 2? That's my quantum system. The quantum system for a superconductor that works with Josephson junctions is that you measure how many Cooper pairs have traveled across this barrier, have quantum tunneled across the barrier. So I'm starting to get in the regime of things that I'm only slightly more knowledgeable than you about. I hope my advisor doesn't watch this video. So like I said, you basically have an LC oscillator. So I should have put more extra slides. I didn't expect more complicated questions. Like Tyler was like, yeah, they're gonna ask you like what's a frequency and like what's a hertz, So you have an LC oscillator, right? And the current is oscillating back and forth like this. And so in a superconducting Josephson junction, you can think about it as the same idea, but it varies by sign of the phase difference across the superconductor. So this idea of a transmon is that you have the inductive part of the LC and the capacitive part of the LC, and they're kind of varying back and forth like this. And when you get down to the really sensitive levels of single photon energies, you can measure it has 1 Cooper pair gone like this or has 1 Cooper pair gone like this. And depending on how good the oscillator, how big the inductive portion is and how big the capacitive portion is, you can tune your transmon to be sensitive to different things. So really inductive transmons are where we want to work, because there's this thing called, I'm starting to get really far beyond your question. Just think about it as quantum tunneling. Every time something tunnels across, the phase changes. So then these wave functions that have the difference between their phase, we keep track of that as our parameter. That's exactly how our superconducting qubits work.
So it's the way that you're citing out specific wavelengths that you're looking for.
So specific wavelengths is referring to the resonators. So the resonators are how we talk to the qubit. The qubit itself The qubit itself, yes, in a way, yes. The way we tune our parameters means that our qubit is very responsive to a specific frequency, but that doesn't really have as much to do with this. That has more to do with how the differential equation works when you have two Josephson junctions and a capacitor. Yeah, think about the two. So the whole chip, the whole transmon, that wavelength that goes through that's the resonant frequency. This is just one Josephson junction. This is where the quantum tunneling happens, and that's where you want to keep track of what has gone where. Question?
You talked about the parasitic effects you deal with your resonator. What kind of effects were those, and how did you deal with them?
Sure. So the question was, I mentioned parasitic effects. What types of parasitic effects are there, and how do we deal with them? So to go back to the image here, so this is our coplanar waveguide or my microwave resonator. So it's cut out of a chip, and the picture is not. Why was this one? Right. So we have a substrate, and so the main one that we talk about is okay. So this one is like the elementary idea of what was going on with parasitic effects. This can be mitigated to a really high level by using non-polarizable elements. So our chip is built on, I want to say, sapphire substrate. So the sapphire atoms are very resistant to polarizing. So they won't polarize like this as much as like any metal would, like aluminum or silicon or things like that. So that's how we dealt with that. And by we, I mean everyone else in this industry. I just showed up. Another source that is actually something that we are currently investigating in the field is this idea that the substrate, even if it's sapphire, all the materials have atoms, right, that have electrons. They have atoms that are grouped together in a specific configuration. And you could talk more about group theory to analyze that, but you could have electrons traveling between different atoms, and that forms two-level systems in some way, right? Let's just start with that as a fundamental. So these form two-level systems, which is fundamentally different from polarization. So the two-level systems that are formed in our chip that we can't control, and also this is what we think it is. This is no guarantee that this is actually what it is. Our two-level systems that are located everywhere in our chip, when we start to power at very low powers, our signal starts to couple to the two-level systems and make them do something called Rabi flopping. So Rabi flopping is something in quantum 1 and quantum 2 that's mentioned like for a day, and then you forget about it, and then it turns out it's the most important thing ever. So I'm kind of venting here. So Rabi flopping is when the two-level system goes up to 1, so it receives energy, goes up to 1, and then it spontaneously decays, goes back to 0. And then it receives more energy randomly, goes up to 1, and then comes back to 0. And it does it at a specific frequency. This Rabi flopping is constantly happening in all of the two-level systems that I write with quotation marks because I don't know what they are. All the two-level systems, Rabi flopping, that causes a parasitic effect of losing your energy and you don't know where it's going. So yeah, that's the main one that we're looking for right now. How do we deal with that? So the idea is, one, instead of powering our qubit at the resonant frequency, we power it by some detuning. We go off of the resonant frequency. And so that's something that's really common in anywhere that you work with anything that oscillates, to be honest. This detuning we can control that a lot better. So I can say I'm exactly 5 megahertz away from my resonant frequency. So instead of 8.7, I'm at 8.695. That's a lot easier than saying I'm exactly 8.7. So with that detuning, I can say, okay, I'm detuned for my transmon, and so I avoid any specific resonant frequencies within that 8.7 regime. And the detuning helps with a lot of other things too that I could only offhandedly talk about. Does that answer your question?
Yeah.
Awesome. Any other questions? Yeah.
So correct me if I'm wrong, but what I was understanding is that you're using these resonators to try to communicate with the qubits while further isolating them to produce noise. Is that the only way that you're trying to account for noise, or are you doing anything for like correction on your data or anything else to like try to improve like noise reduction?
That's a really good question. So the question was, I said that I use resonators to isolate my qubit, and I also use it to communicate at my own control. but is there anything else I do to further take my data and correct it for any outside uncontrolled sources? All right, so fantastic question. That really brings me to think about, for example, the way that LIGO does it. They take a lot of data correction methods to their data because they have so much noise. The amount of noise that we're receiving relative to our signal is not as bad as LIGO's, where they have like, you know, like I have this archaic story that I was told that they had this specific 40 megahertz noise that they couldn't identify, and they found out that it was a woodpecker on the campus, and so they had to get rid of it. So that's how sensitive they were, you know. And you know, it's like through walls, through the earth. Their thing is like inside a vacuum chamber. It's crazy. Okay, so no more deflection off of my experiment. So for my experiment, my resonators are extremely sensitive, as I told you about. So this resonator that wasn't particularly a good one had a Q factor of about, oh, it was awful, it was 20,000. Usually we have them in the millions. So this really, really terrible resonator has a resonant frequency, sorry, has a line width, which is how we describe how sensitive it is, of about 250 kilohertz. What I'm trying to say is that the amount of noise that we get from the environment isn't, you can see it's really, really bad, but we can still make fits to it. And so, long story short, we're not at the place yet where we care about the specific actual values. We more so want an estimate. So I just want to know, is in this case, are the and I didn't explain this entirely, are the resonators on the top that are made of niobium better than the resonators on the bottom, which are made of niobium with a palladium gold plating on top? And I'm not trying to say, okay, is this actually a resonator, you know, like versus LIGO? Is this actually gravitational wave? That's a completely different regime that we're working in. So as for noise correction in my data, I spent a lot of time working on these fits. I don't know if that counts. I tried lots of different algorithms, and I picked the one that made the nicest numbers. So yeah, there's not much noise correction to be done. When it comes to actual qubit measurements, which I'm building my first setup for qubit measurements this week, my understanding is that a lot of the issues that are going to come from that will come from mismatching resonant frequencies. So is my resonant frequency actually at 8.7 or is it different from that? And so on. So yeah.
Well, if you guys have more questions, since we're over time, feel free to come up front. If you're here in the room, make sure you signed in on the laptop if you haven't already. And let's thank Jorge one more time.
Cool. All right. More questions. I love questions. How's it going? So I am going to get flamed, but I only use Python. I think that I'm not doing anything computationally intensive enough to need to use C. If I were to do something computationally intensive, I would which is 90% of the probability, I would leave it to run overnight or like the next day. You know, if it really were that bad, and I don't think it ever will be, I would resort to using MATLAB. Or in even worst case, I would use a packaging like CPython or something. But I don't expect to do anything like that. I'm forced to use MATLAB already, and I'm only using it to interface with the devices that I have in my lab, like the VNA and the attenuator. They all have MATLAB class files that you could just type in Agilent V701A, and it's like someone wrote like 400 pages of how to use this with MATLAB. And then if you try and find it with Python, you'll find like some random person's blog and how they spent like 7 years trying to get it to work with it. So yeah, I use MATLAB when necessary, Python every other time. And specifically, I have a really strong opinion about this, but I use Jupyter Lab 90% of the time because Jupyter Lab keeps you organized. And now there's such a thing as overusing the cells. I haven't decided myself yet. What I like to do is so my advisor, what he does is he copy pastes his like files from one experiment to the next and to the next and to the next. So he has like 5 years or 15 years worth of like files that are all nearly identical copies of each other, but they iterate on each other every time. I see the advantage of that. I hate it because if you do more than one experiment and you change your file from experiment to experiment, it gets ruined. Yeah. So what I've been doing is I put one Jupyter Lab script in every experiment that I do. and I host on GitHub my, I made a library, a Python library that is specifically for resonators only. And I keep the really general code on the GitHub so that I can import it every time I start a new experiment. And if I ever change one experiment, how my resonator class file works, it'll reflect itself on all the other experiments. So it encourages good coding practices, and I'm not like having a 50,000 long Jupyter notebook. I only have like 10,000 long, you know. If you think I'm joking, I can pull it up. I'm so serious. So serious. Should be fine. I have like 20 things open. Ah, here it is. This is my homework that I currently have not done yet. So this is my Jupyter Lab file for my most recent one. I have this library right here. Resonators, this is one that I wrote. And then I have another one that I haven't done in this lab. So I load all my resonator data in this cell, and then I keep it separate, right? And in this cell, I do all the fits and photon calculations. And then I do that. And then in this cell, I do one type of fit. In this cell, I do another type of fit. And then in this cell, I do a plot. And in this cell, I do different Q curves that you saw, that 4 2x2 plot. And that's where it is there. Copy paste it onto my slides. This is the same. This is the same as that plot, but like resonator 0, resonator 1, so on and so forth. And then this is where I'm still working on a different type of fit. Yeah. So this is, I don't even want to know how many lines this is. And this is all the library that I wrote for that. And this library file is 500 lines long. So it's 2 months maybe of coding iteratively on itself. Cool. Question?
I don't know if you explicitly say this. What is the objective of your research? Why is it different from like other microwave resonators?
That's a good question. So microwave resonators are a very old thing that have been used for a really long time. What my research right now is trying to do is specifically this experiment that I ran was I put 2 chips that had 9 resonators on each chip. And then one chip was made of niobium, which is a superconducting material, and had nothing on top. And then the other chip had niobium, but was plated with palladium gold. So the reason why we did that is because I talked about the loss parasitic effect, the parasitic effects that introduce losses. The 2-level systems that Rabi flop and have energy dissipate. Those are much more present in niobium oxide, niobium pentaoxide. So we believe that our big source of our losses are from the niobium interacting with air, forming an oxide, and then that niobium pentaoxide, you can think of it as like a rust. That's where all the losses are happening, all the Rabi flopping. And so one solution we had, okay, well, palladium gold does not oxide, or maybe it oxides less, or the oxide is not as bad. But we wanted to see if that was better or not. And I haven't done the confidence test or anything, but you can kind of see from these plots that in so the higher up, so it's 1/cube. So the lower one is technically better. So in this case, palladium gold is better for resonator 0, resonator 1, resonator 2, resonator 3. In resonator 4, it's not better, it's worse. Here they're about the same, about the same, about the same, about the same. And that's like me staring at it. That's not any confidence statistical analysis, but I'm going to be doing that this week to see if in fact palladium gold was better or not for the chips. Cool. Any more questions? Awesome. Thanks so much, everyone. That was a fantastic audience. I really truly love having everyone here. Thanks again.